Well, good morning. And first of all, I'd like to thank Declan and Mike and the rest, everybody else, part of this network, for the opportunity to present today. This is one of the important days, I think, in the HRB research landscape, the opening of this network in a formal way today. I like your thinking, Declan, that we fill the Gibson, and then just beside us we have the Point. It's clearly next, isn't it? And then we're looking towards, I think out here we have the Aviva. I also notice as a Mayo man you're turning your back on Croke Park, but that's probably completely unfair. So the talks, the translational statistics, this is a definition that we have defined out of the research group in Galway. Feel free to cite this as often as you can. Okay, so this is the first audience participation. That'll be it. That's the only question asked of everybody. I'd like to acknowledge my collaborators and friends and researchers here, all part of this. You'll see the names are, a lot of the names you will know. Amir is one of my PhD students. You'll see some of his work in a moment. But this is a collaboration between the School of Mathematics, our statistics group, and the biostatistics unit. So this is very much this place where we are as biostatisticians, this primary and an enabling capacity of what we do. And I'm going to try and bring all that together in this talk in 4 different ways. So I'm going to define translational statistics in a minute in terms of what we define that to be, why we think it's important. It's in some parts an apology from the statisticians. There's some parts of what we do we haven't done very well. In our primary capacity, we often work very much on the methodology. That's what excites us. We pass over a tool that's then used, and it's used where often you put the responsibility on somebody else to translate the work that we have just built. So there's this kind of synergy between the two. I'm trying to fill in that gap. I'll show you the role the media play here. This is not me having a criticism at the media. It's again just showing you what can happen here if this translational step doesn't work very well. It's well and good then to put out some suggestions of things that haven't been done very well. There's an onus on you to try and help improve that. So I'm going to present 2 different pieces of work that we have developed in Galway. I'll demonstrate a nice piece of software that people might find useful. I will also give you some results of some new primary research we have in biostatistics that I think again might be useful. And then we'll wrap this up with some conclusions. Okay, so translational statistics. It sounds very grandiose, and it clearly is holding hands with the notion of translational medicine, which everybody in this room is very comfortable with. So if you think of translational medicine, the convergence of basic and clinical research disciplines, the transfer of knowledge, benefits, risks, and therapy. So this is very much the bench to bedside. Now, inherent in that will be the role that the statistician will play. So we thought, okay, there's the 2 different parts here. There's a role the statistician plays to make sure that this translational part, this bench to bedside, is correct in terms of having a good discussion at the beginning about the study, the design, all that part, the analysis. But then we said, what about the second usage of the word translational? So I'm using the mathematical word of translation to move. So this is moving from the start of the initial decisions right through to the final trial. That's the statistical part embedded in the translational medicine part. But there's a second play on the word translation, which is how do we translate the results of what we have just done? Remember, clinical research is the only science with an absolute dependency on participation from the public. When we talk about N means people. So there is this onus. If we want people to get involved in the trials we're involved in, there's a responsibility on us to translate the results clearly in words. I'm using words that are accurate and accessible. And there's clearly a different and diverse audience here. We could be translating the results to our collaborators. We're translating our results to the patient, translating the results to our funders, translating the results to the media, and there's different methods there. Okay, so what's the aim of translational statistics? So I said that a lot of the results and a lot of what we do as statisticians, we're more interested in the methodological approaches. That's what excites us. What's lovely then is we get a chance to apply these. So being a biostatistician, you get to play with everybody's data. It's great fun. You get to learn so many things. It's a very fascinating discipline to be involved in. But traditional statistics, or translational statistics, we now want to make sure that these scientific results are useful in practice. So it's this extra skill. We're not taught this as statisticians. We're taught about the mathematical properties of what we do, and then we pass it back. So it's to fill that space. Okay, so I'm going to give a couple of examples, and you'll notice there's a couple of the titles here sound like I'm not being particularly happy about things. So the first, at odds with odds. How often do we talk about odds, and we talk about the results of something in words like odds and odds ratios, and this type of terminology is used a lot. Unfortunately, it's not very well understood. So what am I talking about here? If you want examples, you go to the Daily Mail. I mean, that's not unfair. I mean, it is the health section. But have a read of that. It says, why eating just one sausage a day raises your cancer risk by 20%. So Mike would have said the key word in there is raises. So there's some notion of risk has been increased, 20% increase. What does that mean? Is that a relative increase? Is that an absolute increase? If I eat 5 sausages, will I die? I have just one sausage a day could dramatically increase the risk of bowel cancers, experts say. Picture posed by model. Okay, no reference to beans, chips, all of that seems to be absolutely fine. So anyway, but this is a newspaper headline, fine. So we have to go at the Daily Mail. Now we have the back of the Dublin buses. When I came yesterday, I saw Lotto, bigger, better dreams. Okay, so this is fine, the Lotto, the bigger, better dreams. And what's the marketing behind this? Keywords there, bigger and better. Dreams, fair enough, on the right. The old Lotto, choose 6 out of 45. So as a probability, that was about 1 in 8 million. That's the probability, 1 out of 8 million. So you have one chance if I buy one ticket out of 8,145,000, whatever possible goes. And that's my probability. What's that as an odd? So that's not the same denominator. The denominator is changing now. It's now 1 event against 1 minus the number of events. 1 far, 8,145,059 less. So everybody here knows the difference between a probability, the number of events over the total compared to the odd, the number of events against the number of non-events. In this case, it makes no difference because it's so unlikely anyway. But there is this notion, even the Lotto page talks about odds when they're really quoting the probability. So be careful. As we know, the odd will always be bigger than the probability. That denominator is smaller. So it's a nice trick to make things sound better. Call it an odd rather than a probability. People might know the difference. The old Lotto was what, 6 out of 47. So that's the new one is 6 out of 47, 1 in 10 million. So relatively speaking, what's the difference? You have about a quarter of a chance less now of winning the Lotto than you had before. If we did the ratio of those probabilities, we would call that what, a relative risk. Is it the risk of winning the Lotto? Maybe it depends on your family. I don't know. Should it be the relative chance? So there's this terminology that's happening here. Okay, so if that was your chances of winning the Lotto as a block, that's what it is now. It was about 4.8 million, the jackpot, they're now saying about 6-point-something million. So there's that multiplier in terms of bigger, better. Now, my late mother-in-law played the Lotto a lot, and she always gave out to me because I gave her these numbers. She loved me. And I used to say, she would say, but John, she said, somebody always wins. And I'd say, yeah, Nana, but that's not the bet you're playing. You're playing the bet that it's you, and that's a totally different thing. So then she told, so fine. So then I wanted then to try and come up with some way of describing what are the actual chances of winning the Lotto that might translate to the public. So if you take, again, the classic Lego blocks, you have your 8-piece block, and we're going to line them up end to end from this podium. One of those blocks will have winner underneath it. Okay, so the Lotto that we're playing, the old Lotto, it was the equivalent of lining them up from here to Cork. So that's your chances of winning the old Lotto. Fine, you may take that. Remember, the Lotto is not about chance, it's about dreams. It's a €2 for a dream, so I understand that. The new Lotto, you then have to go out past Clonakilty and get to Skibbereen. So that gives you some sense of translating what these might be. Relative, fine, but in absolute terms, that's the game you're playing. Okay, so that's well and good to have what you might see is not necessarily an example, but at least gives us some understanding about be careful jumping between odds and probability. When does it matter? It doesn't matter if it's a tiny event, but it will matter as that changes. So here's an example about how can 1% become 30%. And this is a very important example. And this was an example that you may have been involved in terms of reading some things without necessarily going after the full story. This relates to some work that the Marine Institute carried out a few years ago in Galway. They looked at a paper, they were interested in the effect, so this is an intervention, the effect of administering this prophylactic sea lice therapeutic to Atlantic salmon just before they migrated. The idea was that this treatment could give protection against sea lice for up to whatever weeks, in this case 9 weeks. So a nice trial. It involved 9 years of data, lots of different rivers, 350,000 fish. Each of them electronically tagged, randomized to control, given this prophylactic intervention. Let the fish off. What will happen, of course, is the gate will register that they've left. They will go to where they go, and they'll migrate to back within a meter of where they are, and you'll register who came back. Fine, very nice trial. This was looking at the effectiveness of this intervention. What percentage of fish, control fish, do you think come back? So I was interested to see. It's about 5%. So about 5% come back. Now I thought, that sounds very small. And they said, yes, it has been gradually declining over the last 12 years, but the percentage that needs to come back to sustain the population, you don't want 100% back. So anyway, 5%. What about those that were treated? 6% came back. Is that an important difference? This intervention has now given a 1% absolute difference. But remember, if only 5% comes back, the 1% absolute difference is now a 20% relative difference. We now have two numbers we can play with the absolute difference and that relative difference. Fine. The model itself, so there was a very nice complicated model, a logistic model, adjusting for everything you could imagine for. The adjusted odds ratio, 1.2. So what's this? This is the odds of coming back for one group relative to the other. It tells me nothing about the underlying probability. It's the odds in one group relative to the other. Fine, this was published. Problem happened then, because this coincided with the time when the government were going to give award a licensee to fish farms out past the Aran Islands. So the anti-sea lice people then, somebody criticized this. This was in the Wiley Journal of Fish Diseases. This piece appeared to say this is wrong. The Marine Institute have made mistakes. What they did was they took the table from, notice the change in title. So they took, I couldn't resist that, my apologies. So they took the table of results and they did a straightforward, like a meta-analysis comparison of within each river, survived, didn't, or came back, didn't, across the two different groups. I presented that as a meta-analysis, and lo and behold, same odds ratio, 1.2, but then said, okay, what if we treated this as a random effect? What if we treated this as, let's look at all rivers as a sample of all possible rivers? The meta-analysis now is giving an estimate of the odds ratio of 1.3. But there was a big warning there. They didn't present this to say that very careful, there's a huge amount of heterogeneity between rivers here. So a random effect here is letting that heterogeneity, the difference within rivers, that's amplifying the effect. So they said, okay, the effect actually is 1.3. Now remember, this is a multiplier of odds. But the piece at the bottom they said was critically, this last estimate is 30 times higher than that reported in the paper, which means an absolute difference of 1% is now being compared to a relative difference of an odd of 1.3. So this clearly isn't correct. We're comparing relative differences to absolute differences. But this was picked up then by the Irish Times, and there was a lot of debate about this. Have the Marine Institute misled everybody? The title was, if you can't win the scientific argument, suppress it. They say it got better. So they say the Marine Institute own figures now show the percentage of salmon killed by sea lice is not 1%, but 30%. Now that clearly wasn't the case. This was comparing the effectiveness of an intervention. It was nothing about the percentage of fish being killed by sea lice. And it certainly wasn't 30%. And there was a damning statement at the end. This is serious stuff. If policymakers and citizens can't rely on scientific data, how can decisions be based on evidence? And this is the place we're in, and we see comments like this. So this is tricky. What happened in the background was the Marine Institute were arguing with Wiley, saying, why did this piece appear without the editors getting it out of the paper, getting a chance to rebut it? This just appeared as it is. So they were arguing in the background, not through the media, through the peer review process. And eventually Wiley came back and said, sorry, you're right, that was never peer reviewed, shouldn't have appeared, it was essentially an opinion piece. Dick Alstrom picked that up then in the Irish Times to say, apology has been issued to the Marine Institute, all is well. It didn't get any of the coverage, as you can imagine, that the criticisms did. So this is serious stuff indeed. And how did this happen? Is it a simple misinterpretation of odds and probability? Is it a misinterpretation of absolute and relative? Have we empowered people by giving results that people may not be able to ingest, maybe not have the skills to report? Was there an agenda coming from a particular research group against this? Was both things happening here at the same time? So this wasn't good. So I'm going to argue that, first of all, chance would be a fine thing. We understand the notion of probability. Every day we make a decision on a probabilistic scale. We call good things chance, bad things risk. Outside of that, it's a probabilistic scale. Keeping things in there, rather than going near odds, is a much more sensible part. people think an odd and a probability are the same. They're clearly not. So once we move into the space of odds, there's this concern about lost in translation. So I'm arguing, first of all, that when we're in the space and we're looking at percentages and proportions, we think in terms of percentages and probabilities. Let's return the results in those ways. Let's get away from odds. Fine. There is a reason why we use odds and odds ratios, and I'll allude to that in a minute, but this is the part where it's like the statistician's apology. Okay, so another example, and I'm going to motivate this particular tool that I think will answer this question through a nice collaborative piece of work we're involved in with Fidelma Dunn's Atlantic Dip Group in Galway. So they're interested in predicting delivery by caesarean section. And we know that there's dramatic increases with the evolution of modern day clinical practice. The OptiBirth trial is playing a huge role here. Lots of different reasons are quoted for this particular increase. So there's lots of different characteristics and data being collected now. And the idea here is, clearly a caesarean section is beneficial in certain scenarios, but there's suggestions that maybe it's been used in cases where it mightn't be. The question I was posed was, we're going to give you a lot of data, in this case over 6,000 women, and we want to build a predictive model for the probability of whether a woman will have a caesarean section, yes or no. Or you could think about it, can we identify what are the risk factors for caesarean section? What are the key variables that help predict the probability of caesarean section? So this is what? A binary outcome variable. Yes, no. What's the classical approach here? Well, if this was the analysis would be carried out, these are the kind of results that you would expect to see. So there's a very cumbersome table. This is the results of a logistic regression. So we're modeling what? Are we modeling the probability of caesarean section? Yes, no, we're not. Because to model a probability is difficult. You're constrained on 0 or 1. What if I change the probability to an odd? I now go from 0 to infinity. The odd can be as big as we want. What about if I change it from an odd to a log odd? I go from minus infinity to infinity. So my y-axis has now exploded from being constrained to 0, 1 to minus infinity, infinity, and you fit all your standard regression. That's what happens. So it's mathematically attractive to a statistician to think in a log odd space because we can fit the general regression armor, all the typical tools in there. That's fine. So what are you seeing here? On the first column, you're seeing those regression coefficients. So anybody who wants to, if you wanted to make a guess now, you could plug in the different values there and work out the log odds. That's not very informative. So as statisticians, we said, oh, hang on, okay, log odds, let's jump back to odds. And this is typically what you get, the odds ratio. So you're looking at this table now, and first of all, my guess is looking down the right-hand side, and you're looking for small p-values. And everywhere you see a small p-value, you say that must be indicative of something. There must be evidence there. This is 6,526. Virtually everything is going to be significant now. Welcome to big data. Significance is no longer a metric. Everything in big data will be significant. Okay, so then you look at the beta hats. So these are the regression coefficients or the odds ratios. And you say big ones are probably important. Everywhere I see a big number there and a small p, that's probably informative. But it's telling me nothing about the underlying probability of a woman having a caesarean section. It's telling me what's the effect of age. It's positive. As age goes up, that seems to be more likely. As BMI goes up, that seems to be more likely. Some categories seem to have more odds associated with them than others. But this is where this would stop. So we try to think about maybe there's a better way of doing this. Maybe there's a better way of unlocking what you really want from this table, which is the underlying probability for any particular set of values that you want. So we came up with this notion of a dynamic nomogram. Nomogram you've seen before, especially I think there's lots of nomograms used in medicine. These nice visual calculators where you can connect different lines together and get some estimate of what you're looking for. So what's a dynamic nomogram? It's a free tool that we have built. We built it in R, this open source language. It's available on CRAN. Anybody who wants to have it can have it. But it's very simple. So ultimately, you'll see in a second, all we do is we put in the model that we want, wrap it around a function, and it's going to do something nice. So let me show you that in action. So here's R. Now, I don't know if you can see that there. You can see here I'm fitting a logistic regression model. So this is the model, the probability of caesarean section, lots of different variables. The model is fitted. The only function you need is dynom. So it says dynom, what was your model? This is not picking your best model. This is deciding whatever model you have. If you want to display it, you then get this. So this picks out all of the different variables that you want. For example, the key variable here, given it was Fidelma's Atlantic Dip Group, was what about a woman who didn't have diabetes? ethnicity, it picks up all the different levels of each factor. It gives you sliders for all of the continuous variables set at the mean and set in a way that you can't predict outside the values. So here's a particular woman, European ethnicity, no nulliparous, I always pronounce that one wrong, female baby, a preeclampsia, we have pregnancy-induced hypertension, macrosomia. Let's just make a prediction. So there's the underlying probability of having a cesarean section for that particular woman. So that comes out at about 20-something%. We can get the numerical summary if you want there, 26%. What about if we were to look at, what if this woman developed diabetes during her pregnancy, gestational diabetes? What's the effect of that particular risk factor? So that has jumped up the probability by a small amount. What about a woman who has diabetes pre-pregnancy? So there's my estimated probability for the woman with diabetes pre-pregnancy. So now we're getting the effect of the risk factor. What this is also allowing me to do then is, of course, I can now look at modifiable risk factors. I can say, what if I was, what's the equivalent of having a, if I was to reduce your BMI, or if we clearly can't reduce age, but we can look at the effect of modifiable risk factors. What's the effect of, say, a smoker to a non-smoker? And then we can get a direct estimate on the probability which we're interested in. So rather than looking at this underlying table itself and try to pick off what an odd might be, we can play for any particular characteristic that we want and get the point estimate. So that's very nice. We have two other tools in here. One is there's the numerical summary, so we can look at the predicted values for the different set of variables that we want. But the last tool here has a model summary, which means the statistician can now look at this. So he or she can say, well, hang on a second, what model did you actually fit here? You've given me a table of results. I have to believe that that makes sense. I can now get under the hood here. So there is an argument to say that any piece of research that we publish, when you have a table there, you should have a hyperlink below it straight to the model nomogram. That's a translational tool. You're now letting somebody interact with the model. You can now start saying, well, hang on a second, this odds ratio that I don't understand, as I start moving my slider for age, guess what? It didn't really make much difference, even though it looked big. It may have looked big because you recorded age in weeks or months or days or years. That's lost to you. So you can get to interact with the different variables and get an understanding of what the actual fitted probability underneath the hood is. Okay, so the second example, and this fits in very nicely with Mike presented a few minutes ago. So now we're going to move into a different outcome. Again, we're going to talk about risk, survival analysis. So any time to event data, any time where we're modeling time to an event. What's the two classical summaries that we have here? Mike put some up a minute ago. We typically plot the survivor function. The second one is we often model this in the space of a hazard ratio. Now this is a ratio of hazards, and the hazards themselves are not on a particularly informative scale. There is so most translational tools focus on, we need translational tools now to answer the key question. If you present yourself to a clinician, the question I want is, how much time have I left? That's the key question. The problem in what we present now is it doesn't answer that question. So I want you to look at this graph. So here's a classic graph. This is a estimates of the underlying survival function. This was the classic Hrb-Crf trial. So this was oncology delivered in an oral form. This is the 1963 seminal trial, and that's still the same treatment that's used now for children with leukemia, Barrett dosage. But look at this. So this is giving you the effect of intervention. This is the proportion disease-free across time. So think of the proportion of the sample surviving beyond different time points, and it looks like the intervention is working. There's some evidence there. There's a p-value given. I want you to try and decide how effective this intervention is. If I was to now map it into something else, this is a particular intervention, the side effects might be fairly horrific. That's what you give it. And I want you to try and decide, should you take the intervention or not? So what's this typical summary here? Typically we give it a median. It's an intermediate survival time. This number that says, well, this is what happened half the cohort. It's the number we feed back to people, and it's probably the least valuable number we can give them, because it's not going to apply to them. Half got beyond, half got before. Most of those before, you would think that there's less time before and there's more time at the end, so it's clearly not symmetric. But that's the number we give back. Second problem with this is there's no evidence and there's no summaries there in terms of variability. It's one of the few areas in statistics where we quote these are two statistics, their estimates of the population survival function, there's no variability now. People say it gets too cluttered. So how could we improve on that? Well, never miss an opportunity when creating your graph. If you have a line and you can color it, great. If you can thicken it, great. If you can blend it, even better. So there's the same graph, and all we've done is we've taken a look at the amount of variability in the estimate, and we've let that fade through. So this is what's known as alpha blending or transparency. And this just tells you, be careful making any inference out to the right there. There's not much data about that. People get very excited by these curves when there's divergence on the right-hand side. There tends to be no events out there. So that's a very nice way of just saying, take that into account. But the problem again is it's not answering the question of interest. It's not telling me how much time I have left. So there's a very useful function that's used a lot by the engineers, and we tend not to use it in clinical research. And this is called the mean residual life function. So what does it mean? It's an alternative summary. It answers how much time have I left. Engineers like to think about this machine has been running for so many months. On average, how much time have I left before I have to replace it? So there's a formula. So the only formula in this talk, thank you. So the only problem here is to get at this, I need the complete survivor function. Why is that a problem? So first of all, engineers use this a lot. The problem here is engineers can run things till they break. We can't do that. Our trials will have fixed follow-up. Lots of people won't have experienced the event, thankfully, by the end of the trial. So we have right censoring. So here's the problem. This is what we need. There's the complete survivor function. We tend to get this red piece. There's that Kaplan-Meier estimator. We're missing the tail. So to be able to activate this formula and get that estimate, that's what the average time remaining conditional and surviving beyond any particular time point. I need that tail. So we have a nice paper just been published, was published this year in Stats and Medicine, the Galway group, where we present this nice hybrid, this flexible estimator. It's using extreme value theory to model tails. There's lots of nice ways to model tails of distributions. So we said, let's apply that to this case, bolt the tail onto the Kaplan-Meier estimator, and guess what? You get a very nice, reliable estimate of the mean residual life function. Where does that leave us? It now allows us to be able to give this graph on the right-hand side to whoever it is we're translating this result to. So notice what's happened. The y-axis now finally has what we want, time remaining, rather than proportion or probability or risk. So this is saying what? At the start of the trial, we can now estimate that the effect of this intervention is about what? 30, 40, 10 to 30-something weeks. So at the start of the trial, that's our best guess. We can now put some quantitative estimate in terms of how much time this intervention is going to buy. What's happening to the control arm? As they go through time, the time remaining is decreasing. That's not good. What's happening to the intervention? As the further you survive, it looks like the more you're going to survive. This is starting to get indicative now of cure. So if you were to present this to somebody and say, well, there's an intervention available to you, to a 75-year-old man and a 20-year-old man with lots of nasty side effects, and you can now say, typically, this will buy you 1 year. You then may make decisions about that intervention as to what a year might mean in those two different contexts. But what you're answering is, you're answering the question you were asked, which is how much time have I left, rather than the probability of getting beyond something from one intervention compared to another, things like that. So I think that's a nice tool. Okay, so to finish then, we have all of these tools now, and these translational tools, and then we have to decide, are they fit for purpose? The statisticians will work on the robustness and the methodological parts of them, but do they serve, are they fit for purpose in terms of, do they work? Do they help translate? Do they help translate to collaborators? Do they help translate the whatever the key message is to our patients, to our funders, everything else? Well, to do that, we're clearly going to have to trial these things. So this is where the network is going to play a crucial role here. And it's by no means obvious what the measurement should be here. I'm trying to trial something that translates something. So there has to be very clever thinking about the type of trials. Big question then is who'd fund these? How would these be funded? Are these funded by, are we both this on as part of a trial? Like the KEDS idea, things like that. So there's but I mean, you can see, is at any point carrying out all of this research methodologically solid, so we're not criticized by the percentage reported earlier of not done correctly. It's, the work is carried out correctly. Is it translated correctly? So there is that component, and that component needs to be dealt with. So to finish, Martin O'Donnell's line. So the most truthful analysis may not be the one that best translates the truth. We as statisticians can often fit very esoteric, computationally difficult models, chasing after second and third decimal places when that might be not what's needed. So there's an onus on us as well that we fit things that are fit for purpose. Fit for purpose means, outside of being rigorously correct, also translatable. I want to make a call out here to Leslie Daly. So Leslie has made one of the biggest contributions in this space in terms of Irish researchers. I know he'd like to be here today and can't. So his seminal book probably changed the way a lot of clinicians in Ireland thought about interpreting statistical results. He was one of the first to get away from the notion of p-values and think about interval and estimation. So I just want to acknowledge his contribution there. So translational statistics, I think, has a key role to play. So this is its own discipline now within statistics, part of the collaborative space that we inhabit. I think dynamic nomograms are very useful. So this means that once you fit a model, you can now interact with it. You can also share the model to the public. They can interact with it. Then it becomes very clear as to what all of these results really mean. We can really get an estimate of the effect of different risk factors and modifiable risk factors. We're not giving a static table with some possibly esoteric results based on ratios of odds. I think these mean residual life plots, so this has become one of our focuses of research in Galway now. We're looking at more of the mathematical properties behind these mean residual life functions, the sensitivity to sensory and things like that. But I think they will become a useful translational tool. The network will play a vital role in informing future trial designs in this space. And I want to finish with this reference and thank you very much. I realize coffee is just about to happen, but thanks for your attention.